So I want to try this example. So I want to integrate 7x minus 2 over x squared minus x minus 2 dx. So we have some kind of a polynomial in the numerator. We have some kind of a polynomial in the denominator. Another thing we notice that denominator is quadratic, polynomial is numerator is linear. So that relationship tickles our happy bone because it's right. It's quadratic, linear. What does that smell like? Yes, so it smells like a potential logarithm, right? But if you try the u sub, you know, the derivative of the denominator is 2x minus 1, right? While the numerator is 7x minus 2, so those are not, they don't differ by a constant multiple. See what I mean? So it doesn't quite match. But what if I tell you that, and you've seen an example like this on your first lap, what if I tell you that 7x minus 2 is the same as 4 over x minus 2 plus 3 over x plus 1? Just somehow I know that. Would that make our life easier as far as computing this integral? If instead of integrating that function, I'll think about integrating this too, because then what's the integral of the first? What? Yeah, so it's 4 ln of x minus 2 plus 3 ln of x plus 1 plus a constant, right? That makes us a little happy. Okay. The whole hang up here is how to go from this rational expression to the sum of the simpler ones. And that's what we're going to focus on in this section, which is probably 8.5-ish or so, called partial fractions decomposition. So we're going to go backwards. Because if I ask you to add these two fractions algebraically, you'll get this. Because first you have to find the least common denominator, which is x minus 2 times x plus 1. So you'll have to multiply 4 by x plus 1, right? And then you have to multiply 3 by x minus 2. So you end up with 7x minus 2 in the numerator. And the denominator is that product. But going backwards that's what we're going to focus on. But the idea is if we can split it into simpler fractions, a whole bunch of natural logs show up all of a sudden. So that's one thing we'll need to learn, how to go backwards. That's called partial fraction decomposition. Another thing that we'll need to remember how to do is, if I consider this example, 2x squared plus x minus 4 over x plus 1 dx. In this example, the numerator has a higher degree than the denominator. And every time that happens, that's still called an improper fraction. Just like when you look at 12/5, that's an improper fraction. You know how to convert 12/5 into a proper fraction or a mixed number, right? How do we do that? How do you go 12/5 into? So you divide. 5 goes into 12 twice, and then whatever the remainder is, so it's plus 2/5, or we just write it like that, right? 2 and 2/5. So we'll have to do the same thing here. We have to actually divide that numerator by the denominator algebraically, and then see what the remainder is. So we have to review a polynomial long division process. Do you remember that fun thing? Technically, if you really remember your algebra, you might remember this thing called synthetic division when you divide by, yes? No. So that's why I want to review the actual full-blown division, because if I always give you a linear, then you can kind of do the synthetic division that works out. But if we do the actual division, do you remember how that works? How you divide polynomials? So you divide the first terms. 2x squared divided by x is 2x. And then you take 2x and you multiply it by the divisor. So this is 2x squared plus 2x. Then you subtract. So what happens when you subtract? Negative x. Negative 4 falls down. Then you repeat the process. Negative x divided by x is negative 1. Right? You multiply again. Negative 1 times the divisor gives you negative x minus 1. You subtract the 2. You end up with negative 3. Right? So that's the remainder. So that means this fraction is the same as 2x minus 1 minus 3 still divided by x plus 1 dx. Right? It's still remainder divided by the divisor. Just like remainder was 2, it's still over 5. That didn't go anywhere. Can we integrate that? That's no problem, right? So that's just x squared minus x minus 3 natural logs of x plus 1 plus a constant. So when faced with improper fractions, when your degree of the numerator is greater than or equal to the denominator, then you can do the long division and then see what's left. So yeah, we're going to get a lot of natural logs in this process. We might actually get a lot of inverse tangents too if you get some irreducible quadratic like x squared plus 1 that cannot be factored. So those are arctangents and so forth. So we'll have fun with that. So this is going to be another one of those scenarios where calculus is rather simple, but the algebra is algebra. Okay? So let me go back to this original problem and actually do it officially, how we can actually come up with this decomposition. So is that what I want to do next? Yes. So that's what we call the partial fraction decomposition. So I want to take 7x minus 2 divided by x squared minus x minus 2. Okay. So think about how we add fractions. We find the least common denominator by multiplying all distinct factors. So we need to know what are the distinct factors here. So the first step would be to factor this polynomial, this denominator, which is easy to do. It's x minus 2, x plus 1. Okay? So that means we potentially were adding two fractions that had x minus 2 in one denominator and x plus 1 in the second denominator. And since all our fractions are proper fractions. If your denominators are linear, then your numerators are some coefficients, some constants. So let's call it A and B for now. Okay, so this is what we're facing with here. If I go backwards, at some point we were adding these two fractions. So our job is to find A and B. Okay? So we need to find A and B. So the way we do this, we actually have to figure out how to add those two fractions. So if I actually add A over x minus 2 plus B over x plus 1, so that means I'll have to multiply the first one by x plus 1 over x plus 1 to get them to the same denominator. I'll have to multiply the second one by x minus 2 over x minus 2. Just by the way algebra works. So we're going to have x minus 2, x plus 1 in the denominator. In the numerator, it's A times x plus 1 plus B times x minus 2. Is that okay? So that means this numerator, A times x plus 1 plus B times x minus 2, has to equal 7x minus 2. Right? I mean, our denominators match, so what I need to really figure out is A times x plus 1 plus B times x minus 2 has to equal 7x minus 2. Has to equal the original numerator. So I'm going to do some algebra. I'm going to distribute the a's and b's, so I'll get ax plus a plus bx minus 2b equals 7x minus 2. So this means that ax plus bx equals 7x. Right? There's no other way to get 7x but by adding a and b. So that means that a plus b equals 7. It has to happen like that. Do you agree with that? And also a minus 2b, those are the constants, has to equal negative 2. So a minus 2b equals negative 2. So that's a system, two equations, two unknowns. So some slight linear algebra appears all of a sudden. We have to solve that system. So how do you want to solve this system? Many ways of solving systems of equations, but it's up to you which one you want to use. Just subtract them. All right, so let's subtract top from the bottom. So a's cancel. B minus negative 2b is 3b. 7 minus negative 2 is 9. Right? That's totally acceptable. Divide both sides by 3. B equals 3. If B equals 3, A plus 3 equals 7. So A equals 4. Okay? So then my fractions are 4 over x minus 2 plus 3 over x plus 1. Right? A equals 4, B equals 3. So you plug them back in there. So you get 4 over x minus 2 plus 3 over x plus 1. And that's what we had originally. And then you integrate it. That's the easy part, the integration. Now, questions in this example, how we did that. This is probably one of the easiest ones you'll see. What? Where your denominator factors nicely into two distinct linear factors. This is the good stuff. and the numerator is something friendly like that. This is a good example. Does that make sense how they work, though? The math behind it, you literally go backwards. You're trying to think, well, how do you add two fractions to get the original one? So you realize you have two constants in the numerator. So then you actually add them, you find the LCD, you get that numerator, you equate the numerator to the original numerator, and then you build a nice little system. And then you solve a nice little system. Fun. Is that right? Any questions on this? Does this make sense? I'll show you a little sneaky way of doing this problem. It's a little quicker. Okay? But the sneaky way does not work all the time. When it works, it's really nice and sneaky. When it doesn't work, you have to build a system and solve the system. But the sneaky way, we'll use it almost every time. At least you can find some of the letters using the sneaky way. So, sneaky way. And I don't even know if your book does the sneaky way. So we all should be able to get to the point 7x minus 2 over x minus 2 x plus 1 equals a over x minus 2 plus b over x plus 1. We should all be able to get to this point. There's no way around that. And we should also find the LCD. What is the LCD? It's x minus 2, x plus 1. Right? So now I'm going to multiply both sides by the LCD. So this is x minus 2, x plus 1 times x minus 2, x plus 1. So everything cancels on the left. You just have 7x minus 2. While on the right side, if you distribute the LCD, x minus 2 cancels, leaves you with a times x plus 1 plus x plus 1 cancels, leaves you with b times x minus 2. Right? Which we had in the previous example. I'll wait till you catch up. But we had that statement, right? Those were the numerators here. Right? These are the numerators. Here's my a times x plus 1 plus b times x minus 2 equals that numerator, right? Here's that statement. Right? It's the same statement. So, how you get to this step, it's up to you. You add them, find the, the numerators, or you cancel the denominators doing the sneaky thing. That's fine. But solving this equation, I'll show you a quick way to cheat. Okay? So, because we know this equation, we'll be able to find the values for a and b to make this true. When that's true, that means it's true for all values of x. No matter what values of x is, this equation will hold. Okay? And now I'm going to do something borderline illegal, but I'm going to say, well, if this is true for all x values, well, why don't I just plug in the x value of my choice? Just randomly grab a number, plug it in for x, and then solve. But I'm going to make my randomness a little, I'm going to do control random pick of x. Let x equal 2. That seems to be very random, right? Let x equals 2. It will also work with -1. Why is that borderline illegal? Because technically x should never equal 2. But we'll just ignore that fact for a minute. I'll just hide that from you. So let x equals 2. See what happens. When I plug in 2, what is this? So it's 7 times 2 minus 2 equals a times 2 plus 1 plus b times 2 minus 2. So you get 0 and b goes away, right? So you're left with 12 equals a times 3, therefore a equals 4. Right? This is the same result as we obtained from solving a big system. So similarly, I can say let x equals -1. You plug -1 for x. So I'm just picking the numbers that kill the parentheses. So I'll end up with 7 times -1 minus 2 equals a times -1 plus 1 plus b times -1 minus 2. So this looks like -9 equals -3b, so therefore b equals 3. So we get the same results, a little less pain, right? So when the sneaky way works, so if you're able to find an x value so it kills one of the letters, then by all means. Because again, like if one of the factors was x squared plus 1, we'll have problems. I mean, we shouldn't go with let x equals I, and then it just gets a little messier. Okay, so don't use imaginary values for x. Okay, just let's stick with real stuff. So anyways, so wasn't that fun? It's a little sneaky way of finding those letters. All right, so now I'm going to put it in a more algorithmic. Most of the time, again, if this was like that, right, I can find A just by putting 2 for B, 2 for X. So, right, B will still go away. But there's nothing I can put here to kill A. But at least if I find B, that will going to make my life a little easier. So I'll use the sneaky way at least some time. But at other times I'll just have to. I mean, if you find B, this will happen. You put, so let's say you put 2 for X, right? So you find A. Let's say A is, well, let's do this. Let's put 2 for B, 2 for X. So what do we get? We get 12 equals 5A, right? So A equals 12 over 5. That's something I'll do. What? Well, because it's 2 squared plus 1. Right? No, it's, I'm just saying if this was, well, the reason why I put the square, because there's nothing I can put for x to kill this parenthesis, right? But if A is 12/5, because we already found that, so this is what I have. Right? Well, you don't have to kill this parenthesis, just put something for x. Just put 0 for x, right? If x equals 0, you'll get -2 equals 12/5 plus, well, b times -2. This is a linear equation. You can still solve for b, right? So you can put whatever value. But there will be instances we're going to have A, B, C, D, E letters to find. So might get a little challenging. Well, yeah, you'll just, you can still, yeah. I mean, you can still use this trick to build a system. Just put 0 for x and put 1 for x. It gives you 2 different equations that both have A and B, and then you just solve. So you're still going to have to solve some systems of equations. Okay? All right, so let's do this in a more precise way. So partial fractions. So yeah, this is about to get all nasty algebraically. So to split, I'm going to write long sentences now. To split a fraction into a sum of fractions, we use partial fraction decomposition. So there's going to be a few cases. So, given a function that's a rational function, so p of x over q of x, where both p and q are polynomials, so first, make sure you're dealing with a proper fraction. So what I mean by that, the degree of the denominator has to be strictly greater than degree of the numerator. If it's not, divide, like you saw me do that. And sometimes you can even cheat a little bit. I have this example written here. So for example, given this problem, x squared over x plus 1 dx. So this is an improper fraction. So I can divide the two, or I can cheat a little bit. Because when I'm thinking about, I need to simplify this fraction. I have x plus 1 in the denominator. I have x squared in the numerator. It would be very helpful if instead of x squared in the numerator, I had x squared minus 1 in the numerator. Because then x squared minus 1 factors into x plus 1, x minus 1, and then I can cancel x plus 1, right? It'll make me happy if I had x squared minus 1. And I'm all about happy, so I'm just going to put it there. But I cannot just put it there. I'm going to add 1 at the same time. Right? Is that legal? So then, really what I have is x squared minus 1 over x plus 1 plus 1 over x plus 1. And the first one reduces. The first one is x minus 1, x plus 1. So that reduces to x minus 1 plus 1 over x plus 1. So we get the same result if you do the actual division. So you can always do that kind of fakeage. Just think how to reduce that. So that becomes an integral of x minus 1 plus 1 over x plus 1. And that's easy to do. So it's x squared over 2 minus x plus natural log x plus 1. Is that okay? It's a lot harder to cheat like that if you look at the previous one where we actually did the long division. Yeah, that's a little messier to cheat. So do the long division.
So when you, I don't remember the long division, but can you divide, if you have the quadratic on the numerator, can you do long division when quadratics on the numerator or the denominator?
Oh, you can do long division. Doesn't matter. As long as the top greater than or equal to the bottom, the degrees. Right?
The top is the same.
So the degree of the numerator is greater or equal to the degree of the denominator.
Okay, that's what I was saying.
Yeah. Because, like, again, just think about the fraction. If your fraction is 3/5, well, it's just 3/5. I mean, you can get the long division, get the decimal, but who cares? Right? But here, if your fraction is 12/5, then there's things to do to simplify that. Is that all right? But anyways, there's also synthetic division. When you divide by linear terms, you can make your division a lot faster. I don't care. Look it up. It's up to you to divide your polynomials. Okay, so moving on. So now, second step, so this is not really the first step. This is the first thing you look for. If you have an improper fraction, fix it. By the time you get, and sometimes you're just done integrating just from step 1. Now, when it's step 2, assume that your fractions are proper, so we're just going to focus on that. So, just for proper fractions. So first, you're going to do, you will factor factor q of x. Oh, we'll cover all that. Yeah. So there'll be cases where it's irreducible quadratic. We'll look at that. So we're going to try to factor. So let's say here's a hypothetical. If factors of q of x are distinct, non-repeating, linear factors, then life is good. So it's all different factors, nothing repeats, they're all linear. Then we're going to do this. Then write p of x over q of x equals, and whatever your factors are, L1 of x plus L2 of x plus L3 of x, all the way to however linear factors you have. And in the numerators, you have some constants, a1, a2, a3, a sub n. So you're going to have all those linear factors in denominators and just constants in the numerators, if that's what happens. And then you just integrate each term. So you're going to solve for all of those a sub I, and then integrate each term. You'll get a whole bunch of natural logs. That's what will happen, if that's the case. So that's the scenario you saw earlier when our denominator factors into just linear terms, non-repeated linear terms. So just do that. Then right. That's just nothing. So let's do an example of this. 1 over t squared plus 3t minus 4 dt. So that's a proper fraction, right? The numerator is less than the denominator. So I'm going to start factoring this denominator and see what happens. So 1 over t squared plus 3t minus 4. So if I factor the denominator, what does that factors into? Right, so t plus 4, t minus 1, the numerator is 2, 1. So that means it's a over t plus 4 plus b over t minus 1. So that's what that rule tells me to do. Put all those factors in the denominator and the numerator just some constants. Okay? So I need to find a and b. So I'm going to use that sneaky thing. I will multiply, well, just focus on this expression. And let's just do this in our heads. Just multiply both sides by t plus 4t minus 1. Just multiply both sides by the denominators. So what will happen on the left if I multiply both sides by t plus 4t minus 1? Just goes to 1 equals a times t minus 1, a times whatever's not there, plus b times whatever's not there, so t plus 4. So you should arrive for this point somehow. Whatever you do, if you add them, find the common denominators, those are your numerators, really. That's what's going to happen. So then we can start saying let t equals 1. If t equals 1, you plug 1 for t, you get 1 equals, so a's are gone, b times 5. Right? If t equals 1. So solve for b. B equals 1/5. Is that okay? So what else should I let t equal to? -4. So now b is gone. So you have 1 equals a times If t is -4, you end up with -5. So a equals -1/5. Is that okay? So b is +1/5, a is -1/5. So I can actually say that now my integral is, let me write b first. I can factor 1/5 out, right, because it's 1/5, 1/5. A is negative, so I'll just have 1 over t minus 1 minus 1 over t plus 4 dt. Is that okay? I can factor 1/5 out. A carried a negative sign, so I'm just making that thing negative. So just integrate that, so it's 1/5 natural log of t minus 1 minus natural log of t plus 4. That's a constant. Questions on this? Is that okay? Okay, so this is one of the nicer cases where your denominator factors into a product of non-repeated, distinct linear factors. Usually distinct and non-repeated, if you have one, it implies the other. But anyways. So another thing that can happen is q of x, the denominator, factors into linear factors, but some of them are repeated. So for example, one of the factors is like x plus 1 cubed. Okay, so it's repeated there 3 times. So if you think about this, don't write this down. Let's say if you were adding blah over x plus 1 cubed minus another blah over x plus 1 plus another blah over x minus 2. Don't write any of that down. What is the least common denominator would be? No. X plus 1 cubed. You don't need the fourth one because the cube is still divided by the single one, right? If I were to add that, my LCD would still be this. Some other block, right? So if now thinking backwards, if I look at the fraction that has this in the denominator, there is no way for me knowing how many different factors of x plus 1 I had, whether it was a cubic and a first power, whether it was just a cubic. Could have been a cubic and a second power, wouldn't change the fact that that's the LCD, right? If I add another one, another block over x plus 1, still does not affect the LCD. Do you agree with that? So if you're faced with a case where you have some repeated linear factors, because your factors should be, if your factors are linear, then your numerators will still be constants, then this thing should be expressed as, you have your L1x, and then it's L1x squared plus L1x cubed up to the highest power of that factor that you saw, and then some other factors, some L2x plus L2x squared, and again up to the highest power. I don't know how to express it here. Up to the highest power. And your numerators are still some just constants, a1, a2, a3, a4, a5, so forth. So if you see a factor to the power of 5, when you look at your q of x and it has something to the power of 5, let's say x plus 1 to the power of 5, you're going to need x plus 1 squared, x plus 1 cubed, x plus 1 to the 4th, and x plus 1 to the 5th. Because potentially, you might have been adding all those 5 fractions. They will not affect the LCD, so you need to look at all possible cases. Okay? So let me do an example. So let's say we have this x squared over x minus 3x plus 2 squared dx. So it's already factored for us. Nice and sweet. Oh my God. Was it really that hard to solve? Let me show you. I'm sure we can do it faster. These are the notes that I have from earlier. This is beautiful. Is this on? This is some linear algebra at work. So here's that problem I have written in right there, x squared. And then this is my solving the system process. There we go. So this is all just, and then it's just some calculus. Some u-subs. But yeah, I'm sure we can do it a little faster. This was a little messy. Isn't that fun? Anyways, let's try to do it faster. What? No, that won't help. So anyways, but what we realize is that x squared over x minus 3x plus 2 squared is potentially this. You need x minus 3 in the denominator, so it's a over x minus 3. You need x plus 2 in the denominator, so it's b over x plus 2. But you also need some other constant over x plus 2 squared. If those are linear factors. If this was x plus 2 to the 4th, you also need x plus 2 cubed and x plus 2 to the 4th. So you need all integer powers leading up to the highest one. So again, let's multiply both sides by the LCD. So if I do that, everything cancels on the left, just left with x squared. Is that okay? Again, I don't know why I'm not writing this down, but can we do this mentally? What happens when you multiply a over x minus 3 by the LCD? Squared, right? X minus 3 will cancel. You'll be left with x plus 2 squared times a. So it's a x plus 2 squared. Is that right? What about the middle one? Right. So one of the x plus 2's cancel. You'll be left with x minus 3 x plus 2 times b. So b x minus 3 x plus 2. Yeah, and then c times what? X minus 3. Because we can do the sneaky thing here for a while. Okay. So let's try. Let's find some of these values. So let x equal what? All right, 3. So if x equals 3, b's and c's are going to go away, right? So if x equals 3, you're going to get 9 equals 3 plus 2, 5 squared 25, 25a. Right? So a, equals 9/25. Well, good. We got that. What else should I let my x equal to? -2. Let x equal -2. Then a's and b's are gone. I can still find c. If I plug -2 for x, I'll get 4 equals -5c. So c equals -4/5. 0. Let's do that. Let x equal 0. So that might get a little messy. But, so what do we end up with? It is 0 equals, a is 9/25, so it's 9/25 times. When you plug 0, it's just 2 squared, so that's 4. Plus b times, you plug 0, you get -6. Right? And then plus, well, minus 4/5 times -3. Is that okay? So 0 equals, I don't know, 36/25 minus 6b plus 12/5. Right? That's a linear equation. It's really up to you how you want to solve that. How do you want to solve that? Sure, calculator, or I don't know. Yeah, this is times by 5/5, right? So that's 60. 60 plus 36, so that's 96/25 here, and I put 6b there, right? So divide that by 6, that should be something nice. Isn't it? Is it nice? Yeah, so it's 16/25. So b equals 16/25. What was I doing there? I mean, I think I just wanted to make a point that, yeah, you should still know how to do it by just solving system of 3 equations, 3 unknowns, because that's what we're doing there. We're just going through the whole linear algebra process of elimination and substitution. And should we do that? Why not? You should still know. Oh, wow, I used to be so mean. I didn't look at the next page. Look at this. This is fun. Yeah, so, oh, shut up. So we did this in class, right? Well, by the way, let me show you what we did. You should still understand what's going on here. So the top line, we all got the top line. Then I started opening up all the parentheses, combining like terms, doing all that fun stuff, and then just grouped it by x squared, x's, and then just a constant. So you see this line right here. So I'm grouping everything with x squared, everything with x, and everything with just no variable. And it all has to equal x squared. So that means the coefficient in front of x squared has to be 1. The coefficient in front of x has to be 0, because there is no x on that side. And that coefficient just has to be 0, because there is no constant. So this is our system. A plus b equals 1. 4a minus b plus c equals 0. 4a minus 6b minus 3c equals 0. So it's a system of 3 equations, 3 unknowns. And then what do? We did substitution. We say a equals 1 minus b. So we plugged in 1 minus b for every a. So we got this. So it's a system of 2 equations, 2 unknowns. And then we simplify that, solve that. C equals -4/5. Then we went back, solved for another one and another one. And then this is the integration part. That's the easy part. And then I just took a glimpse at the next page. And, or you can just do this, which is precisely what we did, x equals 0. So But yeah, that was probably a good 25 minutes of sweat, right? You still get this. So we're not done yet. We still need to integrate. Oh no, here we go. I'll just talk about it. You write this down. There's no reason for me to copy that. Whoever's not here will not get that recorded because the thing only records, the smart board, not that. But the only new thing here is when you have that over x plus 2 squared. So that's your little u substitution, but it's just integrating a 1 over x squared, which is negative 1 over x. Right? So u to the negative second power, you integrate that, it's u to the negative first over negative 1. Right? So you get you don't get a square. And the negative sign became positive sign. That's the big thing. But the rest of them were natural log. Just stare at this for a minute. I have a cup of coffee. But the big thing here is if you have repeated linear factors, you have to consider all powers leading up to the highest power that you see. Okay, so if you see a fourth power, you need first, second, third, and fourth. It gets really messy really fast. Okay, good. All right. What? Oh, well, you want to go back to that? Okay. Yeah. But again, the hardest part is to find the coefficients. The integration part should be easy. That's just natural logs. Sometimes you're about to see some inverse tangents. Because everything we've dealt so far gave us linear factors, which is not the case always. Sometimes when you factor, you might get irreducible quadratics. The one that cannot be factored, the prime quadratics. Are you good? Just take a picture with your phone or whatever. Okay. Yeah, I'm going fast. All right, so the fifth case is when we get irreducible. So if q of x has a quadratic factor, so then follow this idea. So p of x over q of x, you're still going to treat all your linear factors the way we treated them before. Linear denominators get constant numerators. So you're still going to get something like, a over L of x. But plus, if you have some kind of a quadratic, let's say ax squared plus bx plus c, then your numerator potentially could be some linear function. So some bx plus c. Capital B's have very little to do with little b's. Just making sure. Okay? So if you have a quadratic that cannot be factored, then your numerator potentially is some linear function. I mean, your numerator could still be a constant. Then b would be 0 when you solve your systems. Your numerator could just be some 5x, then c would be 0 when you solve the system. But potentially it could be up to a linear. Okay? So let's do an example. X squared plus 3 over x cubed plus 2x dx. Was that it? Okay. So first step, we'll take x squared plus 3 over x cubed plus 2x. We'll factor that. So x squared plus 2 cannot be broken down any further. Right? By the way, if you had x squared minus 2, go ahead and write it as x plus square root of 2, x minus square root of 2. That's fine. Just don't go into x plus I square roots of 2 and all that junk. Keep it real. Okay? So then potentially this is a over x plus bx plus c over x squared plus 2. Because potentially that numerator is some linear function. So again, we're just going to focus on this part and multiply both sides by the LCD. So if I do that, what's left on the left? What? Yeah, x squared plus 3. What about the right side? X squared plus 2 plus? Or, yeah, bx plus c times x. Yes. So go ahead and solve this. See if you can find a, b, and c. I'll pause this for a little bit. What was the easiest one to find? A, right? You just let x equal 0, everything collapses. Well, not everything, but if you let x equal 0, then you just have 3 equals a times 2, right? So a is 2/3. Now, what was the difference? A equals 3/2, yes. Big difference, don't listen to me. So, well, now we cannot just go ahead and start plugging numbers for x to isolate the other one, but let's distribute the thing. Let's see what we're actually looking at. X squared plus 3 equals if x equals c. If x equals c, yeah, yeah, it will work, but it gets a little messy. But look what happens if you distribute. Ax squared, let's just keep a as a, plus 2a plus bx squared plus cx, right? I mean, right away, we see what c has to equal to. What does c has to equal to? 0. Why is that? Yeah, there's the only thing that has x on the right, and there's nothing with x on the left. So right away, c equals 0, right? And you also realize that a plus b has to be 1. The coefficient of x squared is 1, so a plus b equals 1, right? Also, a plus b equals 1, but we already found a, and since a equals 3/2, so 3/2 plus b equals 1, therefore b equals negative 1/2. Let's see. Okay. So then our integral becomes, we found a to be 3/2, so 3/2 1 over x dx, minus, we found b to be negative 1/2, and c is 0, so I can just write it as negative 1/2 x over x squared plus 2 dx. that okay? There is no c, so we can just integrate this. So that's 3/2 natural log of absolute value of x minus, I'll have to do a little substitution here. Can we do it verbally? X squared in the denominator, derivative of that is 2x, right? So if I put 2 over here, that means I need another 1/2 over there. So I'll have minus 1/4 natural log of x squared plus 2 plus a constant. Is that okay? Because I don't want to do the whole u thing, because it's too simple for that. I hope. It should be too simple for that. Just to fake a deuce, it's just, throw another 1/2 in there. So how's this? So again, this sneaky way, it's really beneficial because you can find at least one of the letters fast. And then your system will become smaller, which you have to solve afterwards. Now, how you solve your systems is really up to you. All right, well, let's try this one. It's an integral of x to the 4th plus 1 over x squared plus 1 squared dx. So I'm not making a new rule for that, but we're going to treat repeated quadratic factors just like we treated repeated linear factors. You're going to need all the powers leading up to the highest one. So you're going to need x squared plus 1 with the linear numerator, bx plus c, and you're going to need x squared plus 1 squared with some linear numerator, cx plus d or whatever. But why? Why would I want to do that? Well, but then I'll have to factor it out. I mean, if I put it back in, it will have to go in as a square root of x, right? Because of the square. So it's, but anyway, so potentially, this is already factored, so it's x to the 4th plus 1 over x squared plus 1 squared. So this will be x squared plus 1, and x squared plus 1 squared. These are my factors, so it's constant with linear, linear with quadratics, so like that. Oh boy. We're not going to get into, well, if you think about this, cubics are always reducible. You can always reduce a cubic into a linear and a quadratic, because every cubic has at least one real solution, right? No matter what a cubic is, it will cross the x-axis. If you go to the 4th degree, yeah, you can have an irreducible 4th degree, so then you're going to end up with a cubic in the numerator. Well, we're not going to go that far. This is just going to be an exercise. Because again, doing push-ups, yes. And we don't want to pull a muscle. Is it still not recording? Huh? It's blinking green. Oh, did I not hit that thing? You're probably right. Oh, I was recording. Yeah. On top of things today. That's good. So anyways, same thing. We're going to multiply by the LCD, both sides. So on the left, we're going to end up with x to the 4th plus 1 equals a times what's missing. So it's x squared plus 1 squared plus the whole bx plus c times whatever's missing, which is x and 1 factor of x squared plus 1. Is that okay? Plus dx plus e times whatever's missing, which is just an x. What? Well, c is definitely 0. And is e the only linear one? Yeah, there is cx and ex. So uh, right. That's the thing you want to focus on. Right. So this will give you the cx cubed, right? So yes, c equals 0. You're absolutely right. And then this will give you the ex. And this is the only linear one, right? Is there? Right. There's the cx2, but that's already 0 because this is the only cubic term, isn't it? Will this be the only cubic? I'm just double checking. Is that the only cubic? No cubic, so that's 0. Ex is the only linear, right? That's the only cubic. So c equals 0, e equals 0, so that helps. So you really want to look, because you don't want to, because I know this is 5 variables, right? It's 5 equations, 5 unknowns. But right away we see that e equals 0, c equals 0. We can do something about a, can we? A equals 1, that's the only constant, right? The only time you get 1 is when, you square this junk, it will have 1, and you multiply by a, it will be just a, because everything else will have at least one variable. So from here, a equals 1, right? Now we still need to find, well, then let's distribute this thing. So right now it's x to the 4th plus 1 equals, so let's square all that. So it's x to the 4th plus 2x squared plus 1, right? Then what else do we see? So c equals 0. So we have bx to the 4th, right? Is that right? Plus bx squared. C equals 0, so nothing there. And then plus dx squared. Let me just squeeze it in here. So plus 1 plus bx to the 4th plus bx squared plus dx squared. Okay. So that's nice. What else do we notice? Yeah, so b has to be 0 as well, right? Because you have x to the 4th, x to the 4th, so that makes you happy. Well, that's just an extra thing that you don't need. So that basically implies that b equals 0 as well, right? And then what is d? Well, negative 2. You have a 2x squared and you have a dx squared, no squared term. So d equals negative 2, right? So you don't really have that term at all. B came out to be 0, C came out to be 0. D came out to be negative 2, so this whole thing is just 1 over x minus 2x over x squared plus 1 squared. Is that right? How do we get what? Well, d, because we see 2x squared and dx squared, right? But no x squared. So that means 2 plus d has to be 0, right? So, yeah. So this we can integrate, right? So if you integrate 1 over x minus 2x over x squared plus 1 squared. That should be pretty straightforward. So it's a natural log of x. What's going on there? You have x squared plus 1, derivative of that is in the numerator. So this is just like integrating 1 over x squared, right? And the antiderivative of 1 over x squared is negative 1 over x. Is that okay? Or do you want to substitute and stuff? Do you recognize that this is du over u squared? So the integral of that is negative 1 over u. So that becomes positive 1 over x squared plus 1. The 2x actually, we need that too. 2 is a part of the derivative. Okay? What did you do? Okay. Now, in a hypothetical situation, let's say b was 0 but c was not. If we had, let's say, 5 over x squared plus 1 as part of our problem, if at some point we had to do this, what's the arctangent? So this would be 5 inverse tangents of x. So that shows up a lot when you have, sum of squares things. So with the constant in the numerator, that will give you an arctangent. If that was, it just went away in this problem. But, okay? Let's try. Any questions here? So you treat repeated quadratic terms just like you treat repeated linear terms. I want to do a fun one from here. Is there one that looks, let's do 43. So I want to do this example. So cosine x over sine x plus sine squared x dx. Okay? So it feels like there is some kind of a quick substitution you can do. You have a bunch of sines and a lonely little cosine, right? Because if you let u equal sine x, then du is cosine x dx, right? Feels good. And if it feels good, it got to be correct. So then this becomes du over u plus u squared, right? Well, this looks just like what we've been doing. You have some kind of a rational function that can be factored, right? It's 1 over u, 1 plus u du. So we can do this by partial fractions now. Is that okay? So if we use partial fractions on 1 over u, 1 plus u, so that's a over u plus b over 1 plus u. So do the thing, multiply by the LCD. You end up with 1 equals a times whatever's missing plus b times whatever's missing. And then we solve, right? U equals, let u equal 0. If u equals 0, what is a? 1, then a equals 1. If u equals negative 1, then what? If u is negative 1, then b is negative 1. Right? So then our integral becomes integrating 1 over u minus 1 over 1 plus u du, which is just a pair of natural logs. And then you substitute back, you get natural log of sine x plus natural log of 1 plus minus, right? There is a minus in there, sorry. And that's it. You can put it in a 1 natural log, that's up to you. How's this? What? What switched? I never said that. Let me ask you this question. I have a philosophical issue. Well, I have you for another 7 minutes. Slow down. Philosophical issue I'm having. And I don't know the answer to this. So I'm going to ask you. If I make this a 2 in here, right? So that'll make it, that'll make it 2 in there, right? So what's going to happen? It's going to make it, will that make it 2 in there? Right? So basically all the way down, it's 2 over here, it's 2 over there, it's 2 over there. No issue there. So let me go back. I don't have issue with that. Let me put 2 over here. So it's a 2 over here, so that's a 2 over there. 2, 2, 2. Yeah. How do we solve this system? So u equals 0, a is 1/2, right? But then what do? -2, and then b is -1/2. But here's my philosophical issue. U is sine of x. Can I make it equal -2? Right? I mean, that's illegal, right? The sine is between -1 and 1. So will that be pushing a little rules of set?
You made x equal 1.
Yeah, I know, because right, that's what I mean. Like, we're already breaking a bunch of rules just by doing this, right?
Yeah, you have a problem.
And now all of a sudden, I just thought of it, like, as I was doing this problem, like, okay, 1, I can live with it, but what if it's 2?
Like, it's exactly the same.
Right, it's you know, you're just breaking one more little rule. I mean, you're already going to jail. Might as well make it count. That's interesting, because I mean, because that tells me that, you know, this seems very reasonable. I'm just wondering, can we just, if we do that problem on a calculator, will it just work out with those constants? You know, we're just breaking little rules. But you know what I mean? Because I mean, it's a little shady. I mean, we've been doing some shady stuff. But we just saw that when you do the shady stuff legally, it still comes out the same. But this is a little shadier. Anyways, I'll leave you at that.
But doesn't it appear because of multiplying? Or it would be 2 or
Yeah, but
u is.
it's u is sine, and sine is bounded by -1 and 1. So I cannot just say let sine equal 2. That's just, you know, that never equal 2. Well, because yeah, in the context of a problem, if I forget where that comes from, that if I start here, then there is no issue. But sine x itself cannot equal 2, even in the context of that problem. No matter how hard you try, sine x will never equal 2. Well, but I'm not. I'm saying that sine x equals 2. Therefore, I'll divide by 2. Then, well, but that's what I'm saying here. Sine x equals -2. That doesn't work. Anyways, fun.